Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day, here in my virtual classroom. Step on inside. Welcome to Integrated Math 2, Big Ideas Math, Section 7.2, Properties of Parallelograms. We are in a chapter that involves quadrilaterals, and we're going to see nothing but quadrilaterals the rest of the way. 7.1 involved all different kinds of polygons. You could do pentagons and hexagons and heptagons and so on and so forth and find their interior angle sum. Now we're scaling it back down to just four-sided shapes, the old quadrilaterals, and we're going to learn everything about parallelograms that we can right here, right now. Enjoy some TED 2 in the background while we do this. Let's go ahead and get started with the lecture portion. If you want to follow along with this best as possible, open up your book, find some paper, or download it in the PDF section down below, or description section down below, download the PDF for me, and follow the timestamps. We're going to start with the lecture portion right now. Let's look at core vocabulary, parallelogram. We're going to use properties to find side lengths and angles of parallelograms. Parallelograms have a definition to them, but as we've learned some things with triangle proofs, there's more things that there are more things that are true about parallelograms just because the sides themselves are parallel, and we're going to find out what they are. We're also going to use parallelograms in the coordinate plane. So once we know what they are by definition, we can probably use it based on how we know how to do some things on graphs. Okay, using properties of parallelograms. Parallelograms are quadrilateral, four-sided shape, with both pairs of opposite sides parallel. That is its definition. QR is parallel to PS, QP is parallel to RS. That's what they're telling you there. The theorems below describe other properties of parallelograms. So you're going to hear some other theorems. I'm sure either we get to prove them or they get to prove them in this lecture set using a lot of triangle congruence and CP/CTC. That's a big portion of this. But this is the definition. Anything else that is true about it is by extension of this. Without this, it wouldn't be possible. The opposite sides parallel, both pairs. So a parallelogram has two pairs. There are some that have one pair, which we'll talk about, different section, and there's some that have zero pairs, but still have unique aspects. Okay, so let's see some theorems. There's the parallelogram opposite sides theorem and the opposite angles theorem that says opposite sides of a parallelogram are indeed congruent to each other as well as parallel. So both sets of them, PQ parallel to RS and QR parallel to SP. And then opposite angles are also congruent to each other, angle Q to angle S and angle P to angle R. If that's the case, then we can do things with certain problems. If they give them algebraic expressions, we can set them equal and solve, that kind of stuff. There are other things about the angles I'm sure they're going to be mentioning. We'll have to wait for them. Okay, here is the opposite sides theorem. Basic thing is a diagonal is drawn. A diagonal is drawn here that's QS. Given that it's a parallelogram, that means we know the opposite sides are parallel by definition. Let me move myself here for 1 second. There we go. And, or just over a little bit. So with that involved, we can also, and we don't crack this very often. I don't think we've done this together yet. But you have, and this is what they're mentioning, angle PQS and angle RSQ. Here's PQS and here's RSQ. These are congruent to each other because you have two parallel lines here cut by this transversal. You have alternate interior angles that are congruent. So that makes those angles congruent. And they're going to show another set of angles congruent here. I don't know what they say, but RQS and PSQ, if they said it that way. Also because two different parallel lines are cut by a transversal. Two sets of angles congruent that would only be possible with the both sets of parallel lines. So you have you have angle here with that one. And you can find the side in between congruent to itself by the reflexive property. Because of this, these triangles are congruent using angle, side, angle, side, angle right there. And then by corresponding parts of congruent triangles are congruent, we can say PQ is congruent to RS. PQ corresponds to RS right there. And PS corresponds to QR right there. So by CP/CTC, we can find out those opposite sides are congruent. We can also do the same kind of thing with opposite angles. I'm sure they're going to do that next. Nope. We probably get to prove it ourselves together later. All right, let's go ahead. I'm going to keep myself over here. Let's go ahead and look at some of the examples. Use properties to find the values of x and y. This is exactly the kind of thing I'm talking about. We have x plus 4 is the length of AB and 12 is the length of DC right here. They're going to be equal to each other because they're opposite sides. If x plus 4 is 12, x is going to be 8. I speak fast, I know, it's during this lecture. And angle A and angle C are opposite angles with each other, so they'll also be congruent. Y's measure will be 65. X is 8 and Y is 65. So things like that. Depends on how big and ambitious the questions get. Otherwise, this looks like pretty basic algebra, just based off those. But those aren't the only properties involved. There's the consecutive angles theorem, and so you're looking at this like if this is X, we know this has to be X as well. But then there's this Y that's consecutive with it right here and right here. They're certainly not congruent. No. In fact, they are supplementary. Their measures add to 180. Now, I don't know if they get to, we might get to prove it together here, but basically, it's a same side interior angles thing. Parallel lines cut by a transversal, same side interior angles are supplementary. So any two consecutive angles in a parallelogram are supplementary. The diagonals bisect each other. Here's another one that, once again, looks like we're going to have to play with those proofs. Or, looks like the next page. Next page, we're going to see this proof of diagonals bisecting each other. We've seen perpendicular bisectors, but we always called it as one bisecting the other. When they bisect each other, that means they're both making each other congruent, have congruent parts, and M is the midpoint of both of these segments, PR and QS. So bisecting each other, both of them. Not all of the quadrilaterals do this. Parallelograms do, and any of parallelograms' descendants, which we'll talk about, I'm sure, in 7.3. I think that's the order of them. Here's the diagonals theorem of them doing this. So if you draw, well, let's see, when they ask you to draw it, I guess it's just drawn. Diagonals right here. So given that you have these diagonals here, given it's a parallelogram, we know that you have opposite sides parallel. These ones specifically, they're going to bring up. They're going to do something about congruent triangles. We'll take a look in a moment. Alternate interior angles, QPR and PRS, SRP, and then PQS and RSQ, excuse me. So these are alternate interior angles. Hopefully you can see what that is, and if not, we'll probably get to do more. So two sets of angles congruent. These sides we did not say these sides were congruent yet. It said they're parallel. The parallel was to make the alternate interior angles work. But now we can say this. In the scope of this problem, now that we've shown and proven that the opposite sides are congruent, we can use that fact that the opposite sides are congruent. Otherwise, we'd be proving the other congruent triangle thing to get to here. But we have another angle-side-angle case. Angle-side-angle for two sets of triangles, this one being congruent to this one. And if that's the case, then you can get what? Corresponding parts that are congruent, such as this guy congruent to this guy, and this guy congruent to this guy by CPCTC. That's the last thing that you would be putting there. And that the fact that it bisects it by definition of a bisector. Of course, we're proving it's a bisector, not just that those are congruent to each other. So there we go. There's that proof in a nutshell. Okay, as shown, part of the extending arm of a desk lamp is a parallelogram. I guess they mean, yep, that guy right there. The angles of the parallelogram change as the lamp is raised and lowered. I'm very well aware. I've almost pinched my fingers doing it quite often. Find measure of angle BCD when measure of angle ADC is 110 degrees. So ADC is 110. That's this guy right here where my pen thing is going. And C is a consecutive angle with it. So these two consecutive angles in a parallelogram should be supplementary. If this one's 110, this is 180 minus 110, which is 70 degrees. That's measure of angle BCD. You can call it measure of angle C, right? All right, they got another two-column proof here for, what are they going to do? Prove that opposite, I think it's a proof that opposite angles are congruent. Yeah, something. I don't know. This just might be just a proof of a proof. Prove that angle B is congruent to angle F given two parallelograms here. Well, given that they're parallelograms, they can say CDA is congruent to angle B because opposite angles of, so it's not that proof. Opposite angles of a parallelogram are congruent, and they're also going to say the same thing for EDG and F. They're going to use and these are vertical angles, so they're congruent to each other, so that's why I'm using single marks for both of these. So by the transitive property, we can go ahead and say B is congruent to F with that in mind. Something connects to something connects to something. There's just basically a link down the chain that B is congruent to F by the transitive property. I feel like they're skipping a step in that process. They said CDA, I'll just call it D. Well, CDA is to B and EDG is to F and CDA is to EDGF. I guess you can use transitive property there. I feel like you'd have to do it twice. They only did it once, and I guess that's allowed. Okay, that wasn't necessarily one of the... I feel like we're going to have to do some proofs, basically. That was an example of a proof, not of a theorem, just saying, here's how we can use proof practice. How do we use parallelograms in the coordinate plane? Well, we do know opposite sides are parallel. We know opposite sides are congruent. So we can do things with distance formula. We can do things with slopes. So get ready for some of that. Find the coordinates of the intersection of the diagonals of... so we're going to find out where these diagonals intersect each other right here. Basically, since we know diagonals bisect each other, we're going to find the midpoint of either diagonal to do so. Midpoints is averaging numbers divided by 2, or as you've seen me do in the past maybe. Excuse me, count half the slope, count the half the rise and run as you move over. You know, instead of rising 4, running 7, you can rise 2 and run half of 7, 3.5. So they get 7 halves coming too. We have 3 points of a parallelogram. Find y in the parallelogram. So we have x, w, and z. What we got to figure out now is basically how this thing works with respect to slope. They're showing here you have a rise of 5 and a run left of 2. So we got to rise 5 and run left of 2 from z as well. They got to stay on the same. They have to have the same slope and have the same length. Rising 5, running 2 is hitting both of those at the same time. So y is going to be at 2, 1 without actually connecting all of it. Find the slopes of x, y, and w, z to verify their... Well, I'm probably not going to verify their parallel, at least not through calculations. All the calculations they do, again, I'm going to do a lot of counting for that. So I can count down 1 over 1, 2, 3, 4, 5. So negative 1/5 while they do that. Okay. All right, let's go ahead and get started, guys. That was a relatively fast lecture. Maybe I spoke a little too fast on it, but let's look at the vocabulary and core concept check these 2 questions here. Why is a parallelogram always a quadrilateral, but a quadrilateral is only sometimes a parallelogram? Well, a parallelogram by definition is a 4-sided shape where blah, 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 like opposite sides are parallel. All parallelograms have 4 sides, which quadrilaterals have by definition, but not all quadrilaterals have 2 pairs of opposite sides parallel. And that's a big thing that we're going to be doing quite often, I imagine. I say that because there is largely a book that doesn't tend to do that, where they try and say, is a parallelogram a trapezoid? Is a trapezoid a square? Is this a quad? You know, like that kind of thing. And you do that based off understanding that inheritance that, you know, all fire trucks are red, but red vehicles are fire trucks. And I know not all fire trucks are red, but it's that kind of back and forth. Does the converse work? Flipping it around. Not always, not in these cases. Okay, writing, number 2. You are given one angle measure of a parallelogram. Explain how you can find the other angle measures of the parallelogram. Okay, so one angle measure is going to be something. The angle opposite the known angle will be congruent to that angle. And the other 2 angles, which are consecutive, will be supplementary. So how do I do that? Congruent means they're equal. Supplementary means subtract from 180. So let me write that. Subtract from 180 degrees. And so this one is the same. Keep the same. Keep same. I need a verb there. Keep. Okay. All right. Hopefully you can see that, and hopefully you can now see me, and hopefully you can see. I thought I was watching Ted. Anyway, from here we're gonna go ahead and jump to numbers 3. Oh, there he is. Oh, they're watching Law and Order. Okay, that makes sense. Okay, guys, let's take a look at numbers 3 through 47. 3 through 47. All right. Because there are probably proofs, some parts might be longer than others. We'll see. We'll see if the first stuff starts off pretty easy. I'm unlikely to copy down diagrams to this side as they're over there, unless I need to mark it up more so. So these ones, 3 through 6, find the value of each variable in the parallelogram. I'm going to leave that as is. So listen, straight up, I'm going to write some answers here. X is 9. 9 is opposite, you know that thing, and y equals 15. These are parallelograms, not because they look like it, because they tell us. If they didn't tell us, we wouldn't be able to know. And this is one of those things where we're in the section on parallelograms, so you'll kind of know what to do because you're focused on parallelograms. But what happens on quiz day, test day, review day, when you learn about rectangles, rhombuses, squares, trapezoids, isosceles trapezoids, and kites, and they tell you it's one of them, and parallelogram just happens to be one of the ones, we still know about the opposite sides congruent kind of thing. That's the question at play. So really, really, really try and understand what you have there. Well, I'll help you more as you go, and I know I'm slowing down. But with that in mind, just remember that right now, hey, this is really easy. Yeah, but you have to still know that it is the thing that we're referencing. All right, m plus 1 is 6. I was using the wrong kind of pen there. So m is 5 if you subtract 1 from both sides. N is 12, straight up. Opposite sides congruent once more. Okay, number 5. This time we have, and you can tell, you might ask which ones are is d minus 21 a length or is it an angle? You have a degree symbol, so that's going to be this angle right here that they're pointing to. It's the one closest. And 105 is opposite that. Let's start with D. Let's start with the new, something we didn't yet do. So we have d minus 21 equal to 105. They are opposite sides, angles, excuse me. They are congruent. So I can add 21 to both sides. I'll get d equals 126. For z, opposite sides, once again, congruent. Z minus 8 equals 20. Add 8 to both sides. Z equals 28. I want to bring this up now because I don't know if side lengths will go with consecutive angles later. Angles can be supplementary. Interior angle sum of a parallelogram is 360. But somehow, sometimes, some students tend to do something with side lengths and talk about side lengths adding to 180 or 360. That doesn't happen. So there's no theorem that talks about what the parallelogram's perimeter's got to be and how it compares there. Angles are a way different basis and story than sides. So make sure you don't try and accidentally do something like that. So g plus 4 equals 65 on this one. Opposite angles here once more. Subtract 4 from both sides. You get g equals 61. And then h, 16 minus h is over here, and that equals 7, opposite sides congruent. I can add h to both sides and subtract 7 from both sides, and I'll get h equals 9. H equals 9 right there. All right, so those are the first 4, pretty straightforward. If I didn't talk so much, I'm sure we would have gotten them done a little faster. Let's go to exercises 7 and 8, where we find the measure of the indicated angle in the parallelogram. On number 7, we want to find the measure of angle B. We know it's a parallelogram, and we have a consecutive angle, measure of angle A, right next to it. Measure of angle A plus measure of angle B should be 180 degrees. They're supplementary. They're same side interior angles with each other. If I subtract 51 from both sides, I'll get measure of angle B equals 129 degrees. That is its measure. Put that degree symbol for short. Measure of angle N is also a consecutive angle with angle M. Angle N is a consecutive angle with M. So their measures will add to 180 degrees as well. These angles are supplementary. So 95 plus measure of angle N is 180 in the same light. Let's subtract 95 from both sides, and you'll get measure of angle N equals 85 degrees. Okay. So that's 7 and 8, pretty straightforward with those consecutive bits. Let's see what happens when we include diagonals in the fold, some of the things that we learned. Because there are some things that you're going to learn about other shapes and that won't be true about these. Again, so far what we know are opposite sides are parallel. That's the definition. Opposite sides congruent, both pairs. Both pairs of opposite angles congruent. Both pairs of consecutive angles supplementary. And both pairs of diagonals bisect each other. The diagonals themselves aren't congruent to each other, but they create congruent parts when they intersect with each other. All right, for exercises 9 through 16, find the indicated measure in parallelogram LMNQ. Explain your reasoning. I feel like this is one of the ones where I should copy the diagram over, so I'm going to do that. This is several problems in a row, which kind of feels good if this is more drill and kill. We should probably be able to crack some of these pretty fast. Number 9, we got to find the length of LM. LM is opposite the length of QN. It might be worth marking up that these are congruent to each other there, now that I have this diagram, and that is going to be 13. They're same length. Number 10, let's find the length of segment LP. Segment LP is half of this diagonal right here. This diagonal is half the whole diagonal. This half diagonal means that this is a whole. Remember, these things bisect each other here. So whatever LP is, PN is the same thing. So the length of segment LP is 7, as the other one is 7. And hopefully the markings on the diagram make enough sense. Number 11, we need the length of LQ. LQ is one of the sides of the parallelogram. It's this one right here, and should be congruent to the side opposite, which has a length of 8. So these are the same. They're congruent segments. So LQ is 8. Number 12, the length of MQ. MQ is the entire diagonal that you see right here. That's MQ. Now, the only thing that's labeled is this guy, 8.2. Now, if this is 8.2, then so is this one right here, also 8.2. Again, that's something that a parallelogram does. So MQ is 2 times 8.2. It's 2 of those, which is 16.4. Now we're going to do measures of some angles. Let's look at number 13. Measure of angle LMN. LMN is this guy right here. Now what's congruent to it? This guy over here. Now this guy, we do not have an angle measure for. We have this is 29 degrees, but we do not know that diagonals bisect their angles. In fact, they don't. In fact, as this looks like a parallelogram, that doesn't look like it's bisecting it. This angle clearly looks bigger than this one. No, we're not doubling 29 degrees. And this 100, by the way, is the entire arc that you see here, whereas 29 is just this guy, 100 is the entire guy. I'm actually not going to use 29 to help me here. I will use the 100, however. Given that this is a 100-degree angle, measure of angle Q is supplementary, as to 180 with the measure of angle L. So when we try and find, and I say measure of angle Q, I should be more specific, measure of angle, oh, I'm sorry, where am I getting at with this? I'm sorry, we got to find this angle. Okay, here's where I got with this anyway. Angle M, I'm just going to call it big I angle. Angle M is opposite angle Q, and I started looking at this the whole time. Let's just go to angle M, same answer as Q, and also consecutive with this big L, right? All right, let's go. Measure of angle L, MN, that'll be 180 minus 100, which is 80 degrees. Good thing I was just on that line now. Number 14. Measure of angle NQL. Where's that? NQL. Okay, this is the one that was opposite the other one. So those are congruent, the M and the Q, the big M and the big Q. Measure of angle NQL. That'll be also 80 degrees, given that opposite angles are congruent. Number 15, measure of angle MNQ. MNQ. This is going to be opposite the 100-degree angle that we see right there. I'll give a second marking to that one like that. So this is congruent. MNQ, also 100 degrees. Another little, no. MNQ. M. And then number 16, oh, it's just getting warmed up. Measure of angle LMQ. Here's LMQ. It's this guy right there. Just that part of this angle. Well, remember, this is a parallelogram, which means this side would be parallel to this side right here. And I bring that up because this could be called a transversal. This can be called a transversal in the way that you have alternate interior angles right here and right here. And we know this measure of this angle is 29 degrees. So this will also be 29 degrees. That's going to end up being the answer to that. Hopefully you can see the alternate interior angles for what they are. But those will pop up a lot, especially in proofs and when they want to get you right there in that kind of way. So I'll mark that congruent kind of like this. Boom, boom, and boom, boom. A lot of marking up that we're doing. If one's 29 degrees, so is the other. Measure of angle LMQ equals 29 degrees. And there's a lot more they could have done with that after that, but they're going to leave it there. All right. Numbers 17 to 20, find the value of each variable in the parallelogram. More of the same, but maybe different kinds of processes involved. Maybe you need to solve one before solving the other. We'll see. Number 17, we have that 70-degree angle. No, we could solve either or. Your choice. Let's go alphabetical. 2m is going to equal 70 since they're opposite angles. Divide both sides by 2. You'll get m equals 35. N is not congruent with 70. It is supplementary to it. If n plus 70 is 180, then n is 180 minus 70, which is 110. Like so. Number 18, a parallelogram, and we have 3 variables here. Now B, well, all of these things, there's no one given measurement of its own, like the 70 there. Everything has some sort of variable. B is an interesting case because I can use it with itself. B minus 10 plus B plus 10 should be 180 degrees right here. They're supplementary. They're consecutive angles. This guy plus this guy is going to equal 180. So let's solve for B given that. Negative 10 plus 10 is 0. That's gone. And B plus B is 2B. Divide both sides by 2 and you get B equals 90. Now, this angle isn't 90 degrees. This is 90 minus 10, which is 80 degrees. And this is apparently 100 degrees. Now, we can also use those, right? Now that we have that information, this is 80 degrees. And this is 100 degrees. That can help us answer D and C. You don't have to do the supplement game anymore. You can just go opposite angles. Opposite 100 is 100. Opposite 80 is 80. So C equals 80. And D equals 100. Fancy stuff for a parallelogram. Number 19, we're going to deal with some of the diagonals in solving algebraically. We have k plus 4 as, I guess, one of the diagonals. Whenever it's marked that way, yeah, I assume so. So k plus 4 is this diagonal portion here, and 11 is this portion here. Those should be the same since diagonals bisect each other in a parallelogram. So k plus 4 equals 11. Subtract 4 from both sides, you'll get k equals 7. And then m is 8. Same thing, diagonals bisect each other. So this m, this 8, same length. And then number 20, I feel like we're cruising along, but it's after the error analysis that they really slow down. They're going to hit us with proofs and critical thinking and the coordinate geometry. That's why I want to count slopes and midpoints. Number 20, speaking a little bit ahead, diagonals bisect each other. Let's go for u, then let's go for v. 2u plus 2 is 1/2 of the diagonal. 5u minus 10 is the other half of the diagonal. If I subtract 2u from both sides and add 10 to both sides, I get this. Divide both sides by 3, I will get that u is 4. V, it's expressed as a fraction, or rather division. V divided by 3 is 6. If I multiply both sides by 3, I will get 18, which is V's length, because that's 1/2 of the diagonal. That's the other half since the diagonals bisect each other. So it's really good. You know, when it comes to this parallelogram stuff, I will say this, or not just parallelograms, but doing this. Some of the algebra, like I said, is going to be very basic. The point isn't can you do the algebra. The point isn't even can you notice set them equal to each other. It sort of is, but can you practice setting them equal to each other so you understand what properties exist in a parallelogram? That's the key. It gets you to practice that especially. The graphs even more so. I can poo-poo on graphs when it comes to the time it takes, but what better way to work something off a parallelogram than saying, gee, I need the same slope because they need to be parallel. Things like that, right? Totally there. All right, exercises 21 and 22. Describe and correct the error in using properties of parallelograms. Why, how dare they? Okay, they say because it's a parallelogram, angle S is congruent to angle V. Consecutive angles won't be congruent. They'll be supplementary. So V won't be 50. U would, but I think they want to ask what V is, and we can correct that. So they stated that a consecutive angle was congruent to the angle provided when it should be supplementary to it. Okay, so angle S and angle V are supplementary. Therefore, they're not equal to each other. Measure of angle V plus 50 is 180. So measure of angle V is 130 degrees. Okay, that's what we get there, and that is the correction. Measure of angle U, like I said, would have been a 50-degree angle. All right, let's correct number 22, figure out what's going on. What silly mistake did we do this time? Because this is a parallelogram, GF is congruent to FH. So they're saying that these two are congruent here. Well, diagonals may bisect each other, but their relationship with their numbers has nothing to do with each other. The diagonals bisect each other. They are not congruent to each other, even by pieces. The diagonal, either diagonal's piece is congruent, either diagonal's half is congruent to its other half. Now, how do we correct it? I guess we say because this GF is congruent to what? Instead, we'll say FJ. So diagonals bisect each other. These two will be congruent to each other there. And then HF and FK. So here, instead of saying that, let's say GF is congruent to segment FJ. Like so. Okay. All right, silly errors. Now, there are some, listen, in a rectangle, that would have been true. GF and FH in a rectangle totally would have been congruent. We'll learn those later. This looks like a 3D, this looks like a folded down object, like table, like falling off the table right there. I don't know if that's what they have. Oh, no, these are just parallelograms. I'm thinking in 3D. In exercises 23 and 24, write a 2-column proof. Prove that segment AB is congruent to segment FE in this situation here. It looks like a fold down thing. I just have to see them as parallelograms. So 2-column proof, that's kind of my go-to. Just kind of wish I didn't have to do that. Statements and reasons, what of them? Now, the question becomes, which theorems are we allowed to work off of, given the properties that we know? Because this is not a proof. I assume we can use them all. This is not a proof that... This is not a proof of one of the properties. So we can use the properties in the theorems. I'm seeing a 4-step proof in my head right now. ABCD and CEFD are parallelograms. That is a given. Because they're parallelograms, listen, opposite sides are parallel. Cool. We're trying to prove congruence. We know theorems that use congruence here. We want to prove that this one is congruent to this one eventually, but they're in separate parallelograms. So what we have to do is kind of show that CD exists in both of these things. I mean, not necessarily show that, but talk about where congruency exists in that. Because they're both parallelograms, opposite sides in a parallelogram are congruent. That means segment AB is congruent to segment CD. And segment CD is congruent to segment CD to FE, segment FE. That is a property of a parallelogram. They give a theorem name, opposite sides theorem. Hold on, let me go back and this is probably going to look weird because I'm on a different thing. Parallelogram opposite sides theorem. I guess that's the name I'll say. I could say opposite sides of a parallelogram are congruent, something like that, because that's what it says. Parallelogram opposite sides theorem. Okay, technically a 3-step proof because I wrote both of these at the same time. So that's step 2 with those things being congruent. So if I marked things, I would say this is congruent to this, but this is also congruent to that. Now, AB is congruent to FE by the transitive property. They both share a congruent measure CD that they're congruent with to each other. Segment AB is congruent to segment FE by the transitive property of congruence. Okay, there we go. Okay, that is my 3-step proof because I merged the first two. I merged 1 as 1 and 2 as 1. All right, number 24. We have to do another proof. We have 3 parallelograms this time, a big guy, and then some other 2 that are inside. We're going to prove angle 2 congruent to angle 3 in totally different parts of things. We can't call them alternate interior angles or anything like, or exterior angles, I should say. But we will we'll walk through something. Let's see what they gave us and how we can use it, given their parallelograms. Proof they're congruent. Okay. Statements. I think I know what I want to do with this one. I'm seeing it in my head, especially with the 1 and the 4 where they are. Totally. Okay. Now step 1 is all these are parallelograms. We got ABCD, EBGF, and HJKD. These are parallelograms. Okay, that is a given. Okay, my step 2 here, here's what I'm going to work off of. Just look at the big parallelogram for now. Well, let's save that one for last. Look at each of these ones individually. Look at 1 with 2. Those are opposite angles of each other. 3 and 4 are opposite angles of each other. And then look at 1 and 4 in the big parallelogram, also opposite angles of each other. All 3 sets satisfy the same theorem. What did I call this one? Parallelogram opposite sides theorem. This is the parallelogram opposite angles theorem. I assume we can do these all in one step and just kind of use that after. So angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. And angle 1 is congruent to angle 4. This is the parallelogram opposite angles theorem. So if I were to mark some things up, I'd be able to go like, let's kind of do it in a different order. So 1 is congruent to, let me get rid of that other stuff. 1 is congruent to 2. Let me say 1 is congruent to 4 next. 1 is congruent to 4. I can use the single mark. 4 is congruent to 3. Boom. You can see there's a sense of transitivity here, and the lecture did it as well. I don't think I have to say anything else there. I don't have to see first that 1 is congruent to 3. Normally I would. That sounds like something I should do because I'm not connecting 2 to 3 yet. I'm connecting 2 to 4, and then I can connect 4 to 3. So how about that? I kind of want to do that. 1 is congruent to 2, and 1 is congruent to 4. Therefore, 2 is congruent to 4. Angle 2 congruent to angle 4 by transitive property. See, the book didn't do this. They didn't have the step in between. I feel like you're supposed to include both. And if 2 is congruent to 4 and 3 is congruent to 4, then that means 2 is congruent to 3, also transitive property. I get that your drawing shows all the single things as well, but that's only because the way that it was actually done that you can see that all together. Transitive property. Again, they might do it just in the one step, skip step 3 altogether, and just put into step 4 as it's step 3, but I'll do that to be safe. That's how I would have done it in the past. Okay, in exercises 25 and 26, find the coordinates of the intersection of the diagonals of the parallelogram with the given vertices. Find the coordinates of the intersection of the diagonals of the parallelogram with the given vertices. Let's put in a graph axes set. Wait, what do we have to do? The intersection of the diagonals. Okay, number 25. Okay, let's plot these guys here. We got W at negative 2, 5. X at 2, 5. This is more than just a... Oh, never mind. It's a parallelogram. Y at 4, 0. And Z at 0, 0, the origin. We want to find them diagonals. Now, what we're going to do is we're going to actually draw those diagonals. You don't have to calculate anything to draw the diagonals. You just connect opposite things. Connect these and connect these. Now, this doesn't look like that these are on integer values. It really, really, really does not. So how did they come up with the diagonal stuff before? Actually, how... Oh, yeah, midpoints. I was going to say, did they use slope-intercept form? No, we don't have to set equations equal to each other. We know that diagonals bisect each other. So either of these diagonals, you can refer to their midpoints, essentially. So how about for zx, xz? Let's find the midpoint of segment xz. Either would be fine. And it's going to go like this. From z to x, I'm rising 5 and I'm running 2. Rising 5 and running 2. The slope of segment xz, well, I don't need to say slope, but the midpoint of segment xz is half of that. Midpoint xz is going to be half of 5 and half of 2. The 2 is the run, is the x, so half of 2 is 1, and half of 5 is 2.5, 2.5 like that. So this guy is at 1, 2.5. Y and W should kind of work the same way. But that is the answer. Number 26. See, it's definitely slowed down, huh? Number 26. We have Q at negative 1, 3. I'm not going to label it until I know. See, sometimes you see me wait to write the letters because I don't want the letters to go inside the figure. I don't know where these points are yet. See, I'll put it up here. Q, R, S, and then T is at negative 5, negative 1. Okay. Okay, here's a parallelogram because they told us so. Sure looks enough like one for me to believe it. Let's find where these guys intersect. And remember, you really only need one of the diagonals because we're just talking about midpoints. But let's see if we can imagine where they are so we don't have to calculate anything maybe. Looks like we might have to. I'm going to wager a guess. It's at 0,0.5, but we'll see. Let's go from T to R this time. Let's do a rise and a run. We're rising from T to R this much and running from T to R this much. I forgot to start the robot vacuum in my class. I want to see if I can do that while talking with you guys here. I just have to kind of hit a start button. All right, rising T, 1, 2, 3. Because my students make messes. It's not just my students. I get people coming out lunch all the time. 4, 5, 6, 7, 8, 9, 10. Rise 3, run 10. We got to do half of those. Let's rise 1.5 and run half of 10, which is 5. Yes, that'll be at 0,0.5. That'll be the midpoint of those things. Notice I'm not doing a massive calculation with that. Counting is fine. I mean, they both kind of refer to the same thing. I'm doing half the distances instead of averaging my values, though. That's the difference between the two, and it's a fine one. Okay, we're still going to do some graphs on 27 to 30, but this time we're going to find the missing vertex, the missing point of the parallelogram that's here. So number 27, I have an update available on this thing. Number 27, clean. All right, it's going on its own. I'll finish the video before it finishes cleaning. It takes about 90 minutes to do my room, my classroom. I don't know if I was specific, if I clarified that. My classroom. Number 27, D is at 0,2, E is at -1,5, and F is at 4,0. D, E, F. Because of the nature of a parallelogram, D, E, G, excuse me, we need to find F. Because of the nature of a parallelogram, that last missing point F that we're trying to find, I assume that's what we're trying to find the remaining one, yeah, D, E, F, G, it's going to be somewhere over here, right? It's not going to be like this area. That's not a parallelogram right there. The parallelogram is going to show that D is the farthest kind of opposite angle, point away. And you have to kind of do something based off what is drawn so far, how this would make a parallelogram. So right now, E goes to D, D goes to G. E does not go to G in this scenario because there's an F that needs to go in between the E and the G. Now, how do I know that? It's not just by appearance, right? Because there could have possibly been other parallelograms that would make something happen here. But this says D, E, F, G. And one thing you're going to have to know is that when naming an object, D, E, F, G means from D to E to F to G and back around. If this said D, E, G, F, then it would be a different kind of thing. It would go D, E, G, and F would be down here, right? There's more than one kind of parallelogram you can make in this setup. But this is the one. Or E, G, D, F. Maybe it would be somewhere up there. But D goes to E, E goes to F, etc. Anyway, how does D go to E? Because D is like the G of this thing where it goes up 1 or up 3 and left 1. So for G, we also got to go up 3 and left 1. And we're going to find our F value right there. That's going to complete the parallelogram. F is at 3, 3. That is the answer to that. I'll even connect it for good measure because they say the thing of like confirm that it's a parallelogram. Well, that's the correct slope, and obviously makes the same distance. D is down 2, right 4 to G. E is down 2, right 4 to F. And you might have thought, well, why didn't you reduce that fraction to -1/2? It's not just about the slope. The slope is obviously huge, parallel, right? Maybe that's all you do need to do once you know one set's parallel than the other. It was more about length as well. If one is down 2/4, the other's down 1/2, then they're not the same length. But if you confirm both sides are parallel, then it has to be a parallelogram after that. Anyway, that confirms it. Let's go to number 28. I think we can go faster now. This says DFG. So once again, we're missing E, but E is the missing link from D to F. Like E is in between in that link. So we're going to have to make sure when we graph this thing, we don't just go from D to F in a drawing. That's not going to be allowed. I don't think the book ever really mentioned that thing that I'm talking about right now. Here's D, here's F. See, D and F do not connect. I'm not going to draw a line there. That would be a diagonal. G is at 1, 0, right here. So D, some E over here, then F, then G. We're trying to find that E. Let's do it the same way that as G went to F, as G goes to F this way, D needs to go to E. So G, it rises up 7 over 1, So we got to go up 7 from negative 4, which is positive 3, and over 1, which is right there. We're going to find E. Excuse me, right here. Confirm it. From E to F is up 1, 2, 3, 4, and over 1, 2, 3. D to G is up 1, 2, 3, 4, and over 1, 2, 3. Yep, they're the same. Parallelogram. Oh, what's the ordered pair? Negative 3, 3. Okay. Number 29. Looks like we're all going to find one of the letters at some point. First F, then E, now G, and lastly D. So number 29. D, E, which will connect with D, F, D, E, F do connect. Then we got to find the missing G. It's going to be somewhere down here. From E to D is down 1, 2, 3, left 1. And from F to G is going to be down 1, 2, 3, left 1. It's going to be right there. So we're going to find G right here. It's at 2, 0. I think if it looks like a parallelogram, I'll be happy. That looks like one. I'm happy. G to D, F to E, same kind of slope. Lastly, number 30 from this set, E, F, and G, those will also connect together in such a way, like in that sequence. And we got to find D, the missing link there. So E is negative 1, 4. F is 5, 6. 5, 6. G is 8, 0. Those do all connect, like I said. Then we got to find D based off that. D is going to be somewhere down there. Let's look at what we do from F to G, so we can do the same thing from E to D. Or from F to E, so we can do it from G to D. But from F to G, down 1, 2, 3, 4, 5. Right, 1, 2, 3. Let's go same thing here. 1, 2, 3, 4, 5. Right, 1, 2, 3. D is at 2, negative 1. And let's draw that thing. Make sure it looks somewhat decent. Yeah, again, we can do one of the slopes because the other one's going to have to kind of follow that same idea. So now from G to D, it's going to be the same as from F to E. Okay, in exercises 31 and 32, find the measure of each angle. So they're giving us a description. Maybe a drawing will help. We'll see. I have no idea yet. The measure of one interior angle of a parallelogram is 0.25 times the measure of another angle. So they said find the measure of each angle here. So another angle, it's not going to be the one opposite because those would be the same, right? But 0.25 times. So the measure of one angle, X, is 0.25 times the measure of the other angle. It says find the measure of each angle. Now here's the other thing about this. The angles of a parallelogram have to add to 360. Now, I don't know which one's bigger. Well, X is going to be bigger. Wait, Y is going to be bigger. There are two sets of X, two sets of Y. That's the reason I'm doing that drawing. 2 of the X's plus 2 of the Y's is going to equal 360. So what I get to do here is, this is a system of equations. I get to solve for X and Y with that in mind. So, listen, I could use the decimal as much as I want. 0.25 is also a quarter. If I multiply both sides by 4, it would just make me happier when it comes to no decimals. So now this is going to say y equals 4x, right? Y equals 4x, because 0.25 times 4 is 1. So I can substitute 4x in for y. Boom, right there. Solve for x. 2x plus 2 times 4x equals 360. And let's just keep going with that. 2x plus 8x equals 360. 10x equals 360 divided by 10x equals 36 degrees. That's the measure of that angle. Y, you can find it several ways. You can either find it by the big adding to 360, you can find it by the supplement of 36, or you can say that it is a quarter of y, so you got to multiply by 4. Y equals 4 times 36, which is the same as 180 minus 36. It's 144 degrees. Okay, that's number 31. Number 32, the measure of one interior angle of a parallelogram is 50 degrees more than 4 times the measure of another angle. So I still have that first 2x plus 2y equals 360 I can use, stick with that. But this one, the measure of one of them is 50 degrees more, add 50 to whatever you do, than 4 times the measure of the other angle. So like that. You take the measure of one angle, make it 50 degrees more than 4 times that amount, and you get that one. So x equals this. I can substitute this for x this time, as there's no fractions. I'm not kind of worried about that. So let's work off that system and say 2x plus 4y equals 360. Distribute, solve all the works. 8y plus a hundo and 12y plus a hundo. See if this number's clean. I don't know. We'll find out. 12y equals 260. Doesn't seem like it's clean. 260 over 12, which reduces to 130. Oh, it must be able to divide by 4. 260, 65. 65 over 3 degrees. Should we round? I don't really know. Oh, never mind. I was going to say, hold on a second. I was supposed to add those equal to 180. No. One measure is 4 times. Okay. Anyway, so 65 thirds, not really my favorite number. If I did any sort of thing to it, if I did rounding, I would say it's about 21.6 repeating, like that. 65 thirds is also fine. I'm good with a fraction. You're good with a fraction. So there's the degrees for that guy, for y. X, I don't know if x is going to get any better. I'd rather, instead of doing 4y plus 50 and get common denominator stuff there, I'd rather do the 180 minus thing. They are supplementary in this way. 180 minus 65 thirds is 540 thirds minus 65 thirds, which is 475 thirds of a degree. Assuming I didn't mess anything up, we should be good there. Let's just double check everything's good. Measure of one angle is 50 degrees more than 4 times the measure of another angle. You substitute that in there, distributed properly, combined like terms properly, subtracted properly, divided properly, reduced properly. And yeah, that all looks good. I'm just going to leave them as the exact numbers because otherwise it won't be exact. All right, that's 32. Let's go on. Let's make an argument, or your friend. Yep, your friend. In quadrilateral ABCD, they didn't say parallelogram. They didn't say parallelogram. In quadrilateral ABCD, measure of angle B. Oh, by the way, I'm going to draw this because, 1, I want to label it, and 2, I want to make sure that you understand when they say ABCD, that means that B needs to be next to A, B, and they go C, D, like that. All right, measure of angle B is 124 degrees. Oh, I don't know it's a parallelogram, but I'm still drawing it like it's one just in case. B is 124 degrees, A is 56 degrees, and C is 124 degrees. Oh. Your friend claims quadrilateral ABCD could be a parallelogram. Is your friend correct? Explain your reasoning. Let me redraw this object more into, oh, I don't know, maybe looking at more like this. Have that 124s kind of look more the same. Let's do it more like that right there. Yeah, and then let's get rid of this guy right here because, yeah, the 124s, is this a parallelogram? Now, why did I do this? Because 124s would both be obtuse, so I'm giving you the appearance of what this is. Now, is your friend correct? No. Your friend was correct last time, which I always have to try and remember to see if your friend's correct one time and then not the next. But your friend is incorrect, and this is actually a good thing for me to talk about. This goes back to letter order. Your friend is incorrect because the 124 degree angle measures are not opposite each other. Now, that alone kind of confirms everything already. That alone would dispute that it is a parallelogram. So it's not, but even if they were opposite each other, you'd have to satisfy more things, which it does. The other things that it does satisfy are that A and B, they are supplementary to each other. 124 plus 56 is 180, so that would have worked. If this was 124 here, that would have then been 56. Now D is 56. This is what's known as an isosceles trapezoid. It's not a parallelogram. But now the reason why your friend may have believed those angles were opposite each other. Angles B and C were opposite each other. But But because the quadrilateral's name was ABCD, B and C will be consecutive angles. If they're right next to each other, they will be consecutive angles. You must draw it in that fashion. That keeps things unambiguous. We absolutely know what's supposed to go where. That's number 33. Okay, number 34. Let's attend to precision, shall we? I felt like I did that on that 65 thirds problem, but why not? Okay. Angle J and angle K are consecutive angles in a parallelogram. All right, so next to each other, they'll be supplementary. Measure of angle J equals 3x plus 7 degrees. Measure of angle K equals 5x minus 11 degrees. Find the measure of each angle. I wonder if this is one where it's also a fraction. They did say attend to precision, no rounding. Maybe they're exact decimals, though, too. Or maybe they're whole numbers. Measure of angle J equals 3x plus 7 degrees. Measure of angle K equals 5x minus 11 degrees. And these guys are supplementary. Measure of angle J plus measure of angle K equals 180 degrees. So 3x plus 7 plus 5x minus 11 equals 180. 3x plus 5x is 8x. 7 minus 11 is negative 4. Add 4 to both sides. And divide both sides by 8. That's not a decimal. 23. That's not the answer. That is x. We need to find the measure of each angle, and I'll confirm that it worked properly based off that. So the measure of angle J will be 3 times 23 plus 7. That's 69 plus 7, which is 76 degrees. Now, I could subtract this from 180 to get K, but I want to confirm that this ends up being that guy's supplement when I do that. I want to know that my 23 was correct. 5 times 23 minus 11 is 115 minus 11, which is 104 degrees. Excuse me. Now, 76 and 104 are supplementary. They add to 180, so therefore that looks very good. Okay, number 35, construction. I didn't know we were going to do that. Construct any parallelogram and label it ABCD. Draw diagonals AC and BD. Explain how to use paper folding to verify the parallelogram diagonals theorem for ABCD. Paper fold. Well, I'll explain that first because I can't fold it. Well, I'll explain it when I explain it. But interestingly enough, for compass construction, I've taught through compass construction perpendicular bisectors, angle bisectors, and through that, by extension, medians and altitudes for perpendicular bisector talk. I never taught you how to duplicate an angle measure, so that's something I have to do within this one. So we're going to call this something ABCD. Now, in order for this to work best, I'm going to just go ahead and draw myself a segment. More so, I want to draw myself actually an angle. I make up my own angle right now as we speak. Boom, just like that. Okay. Now, for me, I can draw a parallelogram just by going ha ha ha, but I need to make some certain things parallel the way that they are. The other thing I'm going to have to do is find some certain lengths that I want. Okay. So I have an angle, and I want to duplicate this angle. Excuse me. Here's the idea of parallelograms. Opposite sides are parallel. Now, if you know the converse of the corresponding angles theorem, so let me kind of draw this first. I'm going to kind of try and draw a line that looks like that. The converse of the corresponding angles theorem says if corresponding angles are congruent, then those lines are parallel. So if you create a congruent angle on this transversal with it, then you will have made parallel lines. Once again, I have a line tool that can do that. But for you, how are you going to be able to do that? In order to make a congruent angle, where's my compass tool? Where did it go? There it is. In order to, oh, I clicked it, but there it is. In order to make a congruent angle, what you're going to have to figure out is how much this thing opened by. And in order to find out how much it opened by, here's what you want to do. You want to make, oh, and I'm going to place a point right here where I want to make the other angle. Okay, there's my point. Okay, you're going to make an arc on this one of a different color. Make an arc on this one. Connect both those guys right there because anything will go based on where this thing goes. I might have to extend this side, by the way. Like that. Extend it outward. Now I'm going to go to this pivot on this point. And I'm going to make the same kind of arc. Just copy it over. Okay. And then from the one where it intersects that you can see this thing right here. whoops. I'm going to place the pivot on this part of this arc right here, and I want to now lower this thing and change the width of my arc so that it matches this right here. It doesn't look like a perfect intersection, so let me kind of widen it one. It's a weird snap. You've seen this before with my tool. Widen it one, but also bring this up a little bit more and see if this kind of works out better. Sort of. I'll have to kind of work off that this isn't the best arc thing because it either snaps to 86 or 91. You see that? So I'll have to try and find a way to really make this work right. Let me lower my pivot as long as I lower the pivot of the other one. So, okay, see where that thing crosses right there? And look at how my pivot's beneath. So let's do the same thing. Let's go up to this guy's arc beneath like that. How beneath? I think maybe like that. And then let's draw the same arc. Where this arc is where I'll draw a line through. That thing snapped out of place. I'll just simulate it. Is where that I would draw a line through from this point where I started through there. So now I can draw a line that looks like that right there that would go through that, if that makes sense. And then voila, I've made parallel lines because I made congruent corresponding angles. So that's my first part of this as far as construction goes. Next part is pretty easy. All I have to do is get fixed widths on these sides because opposite sides are also congruent. So on this segment, I can just draw an arc right here from this angle. Draw an arc right there, boom. And then up here, do the same thing, draw an arc right there, and these will be equal widths. This is something that I didn't know as far as how long that length is, but now I can use that, connect them, and because opposite sides are congruent in that way, these two, and because these lines are parallel, that will satisfy all the needs for a parallelogram for me right here. So this is my parallelogram by construction, just by copying the angles. Next time, if I have to do it again, I would do it significantly faster. I can shrink this side down now, to this. I can even erase that other little point right there. And this should be a pretty decent parallelogram construction-wise. Like, oh, I got to shrink a few of these. Shrink this one right here. And of course, I have a parallelogram tool, but if you're doing this problem, you needed to do kind of these things. All right, they said call it A, B, C, D. A, B, C, D. And I won't erase those marks, but I'll make them a little dimmer. Less bright. Less obvious. Oh, I missed one. Okay. Can't really see them. Draw diagonals AC and BD. Explain how to use paper folding. Oh, so here's the thing, right? I don't have mine on paper. So explain how to use paper folding. I don't really have paper with me right now to talk about this, but it's pretty straightforward. The diagonals bisect each other. So if this was done correctly through construction, after drawing these things, remember that I hate when it snaps after I kind of create the line. Okay. Oh. I'll take it. Remember that this is congruent to that, and this is congruent to that. So as far as paper folding goes, hold on. Explain how to use paper folding and verify. So the diagonals theorem says that these parts are congruent right here. What you can do is, if I want to find out that these work the way that they're supposed to, I can fold down this line right here and see that D touches B. Now, well, yes, and see that D touches B. Now, these things right here are not congruent to each other. They don't have the same angle. So these might kind of have a weird overlapping thing. But if I can fold right down here, if D touches B along that line, then I'd be good to go. Those would work. And then same thing on the other side. If I fold down this one right here, I want to know that A touches C. And again, this isn't a rhombus. Or maybe I made it like a rhombus. I'm not sure. If I made it longer, you'd be able to see kind of the chinks in the armor. But that's kind of what you'd look for the paper folding. I imagine that that's all you're supposed to look to do. That might be the only construction problem there as well. It says explain. So I explained it to you in words. Now let's type it out. Fold down the line AC and touch, and D should touch B. Then fold down the line BD and A should touch C as points. Okay. Let's go. Number 36. The feathers on an arrow form two congruent parallelograms. I think I know what that... Oh, here's one. I was going to say, I think I know what it means. Let me draw it. So, sets of parallelograms here. What are they pointing at? Parallel. The parallelograms are reflections of each other, so the line that contains their shared side. So this is the shared side right here that my mouse pointer is on. That's the shared side. Show that measure of angle 2 is twice that of measure of angle 1. This is probably best that I kind of draw my own. I don't need the whole arrow. I just need parallelograms that are opposite each other, a reflection of one another, sharing a side. So let's go parallelogram tool and draw one of these. And I'm going to duplicate it, flip it over, and place one on top of the other like so. Okay, this is what they're talking about. They have this. Now they do have, ooh, something kind of happened to like my mouse thingy once I did the flip. Let's see if I can bring that back. Shoot, I hate when this happens. Okay, well right now my mouse thing isn't there. I might have to figure that out. I'll stick with this problem and then I'll pause it after and kind of fix this. I might have to restart a program. Where's one? One is, I think one is this guy. Yeah, this is weird to write with now that it's that. And then 2 is this guy right here. That whole thing. So show that measure of angle 2 is twice that of measure of angle 1. Well, here's the thing. These are parallelograms. So that means these are parallel to each other here. And if these are parallel, then, and I'm going to kind of draw a dotted line right here. 1 and this part are congruent to each other. And that guy's half of 2. These are alternate interior angles right here. The measure of angle 1. See, now this little thing comes up. That's not what I want. Measure of angle 1 equals half of measure of angle 2 by the alternate interior angle theorem. Those are alternate interior angles with those parallel lines. Therefore, and because these... I need to know. I need to know to say that that's exactly half of 2. That's something that you can't just say it's half. Because of parallelogram, you can kind of say something with that. I'm trying to think of how I can officially conclude and say that. I know it is. I just want to think of what I want to say with that. Because it's a reflection. By reflection, that's the whole thing. I think that works. Therefore, if I double both sides, measure of angle 1 is measure of angle 2, or the way that they wrote it is the other way. That's the multiplication property of equality. I doubled both sides, and that's kind of why. So again, there's something I could probably say that measure of angle 2 is double that of either one of these, but by reflection, but they didn't really do that. Let me pause just for one sec, because as you can tell, just this mouse is popping up instead of my pen thing. It's actually kind of hard to write with, and for you, it may be more of a distraction than not. Hold on. Okay, and I was back in a flash. Okay, number 37. Proving a theorem. Oh, there's another proof. So 2 proofs in a row. I shouldn't have looked ahead. Use the diagram to write a 2-column proof of the parallelogram opposite angles theorem. So yeah, we never did prove that one before. Now, I don't think we have to prove both sets of angles congruent, because if you just drew the other diagonal, you would repeat the exact same thing but with different letters, or just change the letters around. But with this diagram, and I'll keep the diagram there and I'll mark that one up. But yeah, we're going to basically prove the 2 triangles are congruent. We can use the same ones that they used before, and then by CPCTC, we can say that those... Oh, we do have to say B is congruent to D with this, with that diagram. Why? Why wouldn't they let me just draw the other? Interesting. Trying to think where I want to go with that. I'm going to have to use angle addition postulate. Okay, there are a couple things I have to do with the B and D part. Let's start with A and C, though. Unless there's a faster way for me to say what I want to say in that last part. But that's neither here nor there. Let's go. ABCD is a parallelogram, given. Of course, naturally. Now, I feel like they don't want us to they don't want to let us use the opposite sides congruent thing. Excuse me. I think we're allowed to use it because otherwise I think that's going to take too long otherwise. I can say AB is congruent to CD and BC is congruent to DA and, all that kind of stuff. So we're going to work those by that other theorem from before. It was proven at one point, so we just go from there. So AB is congruent to CD and BC is congruent to DA. BC congruent to DA by the parallelogram opposite sides theorem. Now, you can't use some form of angle side-side, so I can't do alternate interior angles and say those, but I could have led into those ones. I wonder if I should have just done that one to begin with, because I need to use those. You know what? Let me redo that step. I think to prove angle B, listen, I'm going to prove angle B congruent to angle D first. I'm going to prove angle B congruent to angle D first. If I do a kill two birds with one stone, I was going to do this by CP/CTC, but I don't think I have to. Let's state that these opposite sets of sides are parallel by the definition of a parallelogram. So let's start with that. Let's say AB is parallel. Segment AB is parallel to segment CD, and then segment BC is parallel to segment DA. That is by definition of parallelogram. Because we know that, we can use the alternate interior angle stuff and then say that this angle is congruent to this one, alternate interior angles of those parallel lines, and then these parallel sides here, alternate interior angles right there for those to be congruent. So we got an angle case, and we're going to find the side in between congruent and do all that. But before I do the congruent triangles, I want to talk about this stuff here. So we say angle ABD. The only problem is writing all these letters. Angle ABD is congruent to angle CBD. That's the double marked one, CDB. And angle ADB congruent to angle CBD. That's the alternate interior angles theorem because the lines are parallel. Without that, we couldn't have said that. So before I do the congruent triangles and do the A congruent to C, let's do B congruent to D. We have those sets there. That also means we have equal measures. Now, I don't know if what I'm going to do is going to be called a substitution here eventually. I guess it will. I want to say that the measures of these guys are equal now. ABD is equal to measure. I feel like I shouldn't have to do all this to prove those angles B and D congruent. I'd rather draw the diagonal AC for it on its own, or only use one proof and then say therefore it should work for the other, because it should. So I don't know why they're making us do this, but we will. Measure of angle ADB is equal to measure of angle CBD. Or maybe I'm missing something in my writing that I don't necessarily need to know. This is the definition of congruence. Basically, it's the same thing of what you saw above, except now it's measures of. Because what I'm going to do is talk about how they add together to equal the same thing. I'm going to talk about how the measure of angle ABD, I'm going to say how this plus this equals the whole thing, and this plus this equals the whole thing right there. And then do a way of saying that those are equal to each other. Measure of angle ABD plus measure of angle CBD equals measure of angle, this is not enough room, measure of angle ABC and measure of angle ADB plus measure of angle CDB equals measure of angle ADC. This is the angle addition postulate. Now I want to do some sort of substitution here. Or some way of saying that these guys equal each other here. because ABD equals CDB, ADB and CDB equal each other, and because CBD and ADB equal each other, then I could almost do a substitution of sorts and write that out in that way. I could take these and plug them into that, and then it equals the other. I don't know if the way that I'm writing all that's right. I just now want to find a way of saying that these now equal each other. I want to kind of cheat and do the same thing that the book did. Say transitive property in a premature state without stating too many things in one. There's a substitution transitive property that eventually, because this thing's making me do a proof that I don't think is required for this. Measure of angle ABC equals measure of angle ADC. The big guys, ADC. Those are the big guys, B and D. That's why I feel like this is kind of weird, because this says B and D, but there is no such thing as B when there's a diagonal there. I feel like I'm going above and beyond in this problem when I shouldn't be. Maybe you can skip and ignore everything I'm doing from 4 onward until I stop. I'll kind of highlight what this area is as kind of the weird part. I'm calling this transitive property of equality. Basically, I have things that were equal to each other, and then they added to equal other angles, but those angles have to be the same because those bits are the same right here. That's my version of transitive property. Maybe it's substitution. That's where I'm kind of lost in it. Okay, if that's the case, then angle ABC, which is angle B in my eyes, is congruent to angle ADC or angle D by, once again, definition of congruence, bringing it back. There's something there that I don't know if that link is going on the way that it is. So that's one of them. That's one of them right there. Not in the way that I would have loved to do it because the diagonals, I feel like I didn't need that at all, and I should have only proved the other one. I'm sorry that I keep saying that over and over, but because it's presented to me like that, I got to call it out. So the 4 through 7, if you want to kind of skip its madness and let's just prove the other one together, then yeah, then we can do that. So ignore that. Go from 3, where I have the markings of congruent stuff there. Now, because those angles are congruent, we can also talk, not because, but we can also talk about how this segment's congruent to itself, BD congruent to DB, by the reflexive property. This is the official way I really wanted to do this to begin with. Reflexive property of congruence. Now we have an angle side angle case for these two triangles. So I can say triangle ABD is congruent to triangle CDB by angle side angle. The side is in between those sets of angles. And then that means angle A is congruent to angle C. Those are corresponding parts. You can see I wrote them as the first letters. They are parts that correspond. Angle A is congruent to angle C because corresponding parts of congruent triangles are congruent. That's the second one that I want there. So like I said, I would have loved to have just done B and D with the exact same 1, 2, 3, 4, 5, 6 steps, but instead having the parallelogram go like that, but then the diagonal is here instead. Sorry if that's getting cut off. Like this, but instead the diagonal is going here instead. And then I can just do the same thing with B and D and just use alternate interior angles, reflexive property, congruent triangle, such and such. But they said use the following diagram. So, You know what the problem is? I probably should have done that. Okay, time out. I probably should have done that. Notice they never said BD is a diagonal. They just said this is a parallelogram. So I'm missing this draw BD as a diagonal. Okay, my proof's a little wonky then. They said use the diagram. Why did they draw the diagonal for me then? I would have happily drawn the diagram myself. All right, let's do another theorem. Let's hope this is not nearly as awful as me calling out the book for something the book is probably not even their fault. Use the diagram to write a 2-column proof of the parallelogram consecutive angles theorem. Okay, so this is the, I guess I'm allowed to use it. This is the same side interior angles theorem. I think I can say 3 steps on this. Maybe. They do have X's and Y's. I'm going to think about that now. I thought we got to go without this. Oh, x plus y is 180. Yeah, this is fine. We can do this. Okay, so 1 PQRS. I was gonna say triangle PQRS. Triangle PQRS is a parallelogram. What? PQRS is a parallelogram. I was gonna put true, given. All right, 2. We're gonna do the parallel thing from before. We only need one set. So I'll just say these two are parallel here. That's the definition of a parallelogram. So QR is parallel to SP. That's definition of parallelogram. Okay. Now, if those are parallel, then that means you have, I'm going to kind of draw this thick so you have an understanding of it. I got 2 parallel lines cut by a transversal. Ignore anything in black, just look at the blue. 2 parallel lines cut by a transversal. That makes these same side interior angles here. Same side interior angles are supplementary. So angle P and angle Q, for example, is one that I could mention. Angle P and angle Q are supplementary because those lines are parallel. This is the same side interior angles theorem. Just like we had an alternate interior angles theorem when those are congruent, these are supplementary. If they're supplementary, their measures are, their measures add to 180. Now, I don't know if I have to call it measure of angle P plus measure of angle Q first, or if I can just go straight to X and Y. So X plus Y equals 180. X degrees, Y degrees, 180 degrees. Q is the X, P is the Y. I hope that that's okay that we're doing that. That's definition of supplementary angles. So if those are their measures by nature, I can just write that. So I'm good on that. All right. Number 39. Let's see if we can kind of get out of proofs here for a little bit. The sides of parallelogram M and PQ are represented by the expressions below. Sketch it and find its perimeter. Well, I can't go without sketching it because they do say sketch it, and I think it's worth it that I do anyway. So number 39. I got this guy. Why do my parallelograms always look the same? M, N, P, Q. You got to go in a specific kind of order. Wherever you start, just work around the clock. MQ is negative 2x plus 37. QP is y plus 14. NP is x minus 5. MN is 4y plus 5. Whoa. Sketch it and find the perimeter. When we solve for x, we'll plug in the x's, solve for y, plug in the y's, add them all up, and we get our perimeter from that. And unfortunately, they use the letter P, so I can't use P for perimeter after. So, parallelogram, set opposite sides equal to each other. The x's really have nothing to do with the y's in these cases. We just do what we do based on the setup of the problem. Add 2x to both sides. Add 5 to both sides. Divide both sides by 3. You get x equals 14. We're going to use that later. For y, I got 4y plus 5 equals y plus 14. Subtract y from both sides. Subtract 5 from both sides. And divide both sides by 3. You get y equals 3. Now we're going to be able to find all these lengths here. We're going to be able to do mn. Mn is 4y plus 5. 4 times 3 is 12, plus 5 is 17. Let's do NP, which is x minus 5, 14 minus 5, which is 9. Now, the other two are just the same lengths. It's going to be 17 and 9 for the next two. Like for P, for QP, QP should be 17 as well, because this is opposite the MN. Let's just see if it works. Y plus 14, 3 plus 14, which is 17. And then the last one should be 9. That is MQ. MQ is negative 2 times 14 plus 37. This is negative 28 plus 37. 37 minus 28 is 9. So the perimeter is going to be 17 plus 9 plus 17 plus 9. Or double 17, 34, plus double 9, 18. Whoops. 34 plus 18 is 52. There are no units involved, so 52 units is the answer. Okay, let's move on to number 40. Problem solving. In parallelogram LMNP, the ratio of LM to MN is 4:3. Find LM when the perimeter of parallelogram LMNP is 28. Number 40. Let's draw it. L, M, N, P. Nothing's drawn to scale. I'm just drawing this thing out. It says the ratio of this is 4:3. That means whatever of LM to MN. So whatever this is, it's not 4 times bigger, but it's 4:3. 4 times some amount and 3 times some amount. So we can work it out that way. So we can say that the perimeter, oh, they have a P again. So we can say that the perimeter is 28. They say the perimeter is 28, which is the same as adding the 4x's with the 3x's, like that. And then we want to solve for x and then substitute it for LM's 4x to find out what that all is. So 4x plus 3, so 14x. 14x is 28 divided by 14, get x equals 2. So the length of LM is 4 times 2, which is 8. It's not really a guess and check problem. They don't have units, we're going to leave it. Okay, 7 more. Abstract reasoning. Can you prove that 2 parallelograms are congruent by proving that all their corresponding sides are congruent? Explain your reasoning. No. Triangles are unique in that way, but the angles can bend in certain ways to not make that be the case. That all their corresponding sides are congruent. No. It's okay. So 41, no. It says explain your reasoning. A counterexample is always a good one, but no, because if any of the angles change, then it becomes a completely new parallelogram. Basically like this. If I had, because I'm going to make one kind of more, well, I had the right parallelogram shape, so let me go back to it. So I could make a parallelogram that, let's say, kind of looks more like, oh, I guess I can't stretch it. Oh, well, okay, then I'll do this. I'll make that one, and then I'm going to make a rectangle. We're going to learn this later, but a rectangle is a parallelogram of some breed, of some ilk. So both of these, oh, they might not have the same lengths. So both of these, let's pretend, have the same kind of lengths all over, as in this, and remember, a rectangle is a parallelogram. Let's say that this was 3 and this was 7 and 3 and 7. Well, this could also be 3, 7, 3, 7. Corresponding sides are congruent. That doesn't mean you can't change the angles and make those things go up, or, you know, even less parallelogram, like whatever. So no, you can't guarantee that. Just proving by counterexample, just with the drawing and the concept. Triangles, yeah. Triangles are unique and special in that way. Number 42. They want to know how we see it. The mirror shown is attached to the wall by an arm that can extend away from the wall. Kind of. In the figure, points P, Q, R, and S are the vertices of a parallelogram. This parallelogram is one of several that change shape as the mirror is extended. So it kind of like flexes in and out. What happens to measure of angle P as measure of angle Q increases? So as this kind of stretches out more, as Q gets bigger, P is going to have to get smaller. That's just, it's not only nature of the thought of what it would look like, but parallelograms, consecutive angles are supplementary. So measure of angle P decreases. Oh, I guess I have to explain it. Measure of angle P decreases. I'm going to use the parallelogram reasoning because angle P and angle Q are supplementary. If Q increases, then P has to decrease as a result, right? They still have to add to 180. I'm just saying because they're supplementary. I've kind of explained the rest to you. Part B, what happens to QS, the length of the diagonal, QS as measure of angle Q decreases? So if measure of angle Q decreases, this is that part going like that. So measure of angle Q up top right here is getting smaller, which means those get closer, but it looks like that diagonal stretches more. So QS gets bigger. Now this is kind of, listen, this is a little bit of You know the section that we did before on the triangle, larger angle theorem, stuff like that? If Q decreases, then P increases. And if P increases, if these lengths stay the same, the side opposite of that thing is going to get bigger, right? So QS gets bigger because measure of angle P gets bigger. Now that just goes with the thing that we saw before. So I'm really trying to give math reasons, not saying because look at it, it does that. Look how it gets bigger. So there's that. Part C, what happens to the overall distance between the mirror and the wall when the measure of angle Q decreases? Explain. The distance decreases. The overall distance decreases. Now this is because there are, hold on, decreases. Because the lesser angles bring all of those closer together. Because the parallelograms become closer together as this shrinks. It basically makes everything steeper, which makes that, things like that. Okay, I don't think we have to do any more graphs. All right, number 43, mathematical connections. In parallelogram STUV, anyway, that's how I see it. In parallelogram STUV, measure of angle TSU, I'm going to copy this one over. Looks like one of those. I got to fit things in there and play with it. Did that copy? Oh, there it goes. Measure of angle TSU is 32 degrees. This guy. Measure of angle USV, right there, is x squared. Hey, quadratics, x squared. Measure of angle TUV, this whole thing, I'm going to mark it like that, is 12x. And angle TUV is an acute angle. Find measure of angle USV. USV. So we got to solve for x, basically, right? Here's what we got. Opposite angles of a parallelogram are congruent. So this entire angle is going to be congruent to that entire angle. So this is angle addition postulate. We can add 32 and x squared together. 32 plus x squared. That'll equal all of that, which is the 12x over here. Now, I'd like to subtract the 12x to this side, write this in standard form. This goes back to some algebra, for sure. This is factorable. This factors to x minus 8 times x minus 4 equals 0, and we get the answers by zero product property, x equals 8 or x equals 4. They did mention that the measure of angle TUV is an acute angle. Either of these would have worked, but if you substitute 8 into 12 times x, 12 times 8 is 96. That's an obtuse angle. So 8 is going to be out, and 4 is in. So x equals 4 is in because 12 times 4 is 48 degrees. That's not the one I need, though. I need the measure of angle USV. Measure of angle USV is x squared, 4 squared. That's 16 degrees. Good problem. Good problem. I like it. Back to some quadratics. All right, number 44. Last 4 problems. Oh, I see the bottom one's approved. Thought-provoking. Is it possible that any triangle can be partitioned into 4 congruent triangles that can be rearranged to form a parallelogram? Explaining your reasoning. Thinking the picture in my head, I believe the answer is yes. Now, let me just kind of draw that and explain to you what it's saying, and see if you feel that you can work it out in that way. So if I have a triangle like that, it says partition into 4 congruent triangles. That means kind of like go through the mid-segment, or draw the mid-segment triangle, if you will. So like this. So I made 4 triangles that would ideally be congruent. And what they're asking is, could I chop one of these off? Like take this guy here, chop it off, boom, flip it over, place it down here, and then suddenly it ends up looking like, like this, right? And then it makes a parallelogram. So now instead we have that guy as the parallelogram, if you can kind of tell right there. Boom. So ignore the other one. It shouldn't be a problem. I'm trying to think on how to explain the why of the matter, though. If you're doing into congruent parts, then this is a mid-segment. If it's a mid-segment, this part flips over and becomes that. The part that joined up there, or the part that was up there, goes to make that. And then this part that is a mid-segment of this goes over to become that. It gets the opposite sides congruent and attaching with each other. Now, this triangle is very isosceles, but that doesn't change what you do in a mid-segment fashion. So there should be nothing wrong with it. I just need to find a way to explain that with regard to the triangle stuff. Well, listen, the triangles are congruent. No matter whether this is isosceles, whatever or not, the triangles are congruent. So you're going to be getting sets of opposite sides congruent. They didn't say to form a specific kind of parallelogram. They said form a parallelogram. If opposite sides are congruent, you do have a parallelogram. That's a for sure, for sure. You also have corresponding sides congruent in such a way that you have opposite angles congruent because they're all congruent triangles. So this would have been congruent to that. Flipped over is congruent to that. Somewhere I got to mention alternate interior angles. Like that angle is congruent to this one, but that doesn't matter about. That's not alternate interior. But this is alternate interior. Yeah, yeah. The answer is yes. Just because the congruent triangle thing. Yes, because the congruent triangles will will continue to satisfy some of the parallelogram properties such as congruent opposite sides and congruent opposite angles. I don't know. I just based on the appearance and stuff, that's going to work. Okay, number 45, critical thinking is a graph. Points W, X, and Y are three vertices of a parallelogram. How many parallelograms can be created using these three vertices? Find the coordinates of each point. That could be the fourth vertex. So notice that they never mention, they say three vertices of a parallelogram, but they do not specify. This is where I was talking before. I forget which problem number. But they do not specify which ones you connect. So this is where I can like draw this several different ways, and I might just copy paste three different graphs or something. So W is at 1, 2, X is at 3, 6, and Y is at 6, 4. 6, 4. So W, I have to be careful where I draw these things because there are just so many different ways that you can place this. X and Y. I'll try and keep them out of the way. If you don't know what I mean yet, check it out. I think you can do at least three different things. I'm going to copy, paste, and copy, paste. So here's the thing. There's no saying whether W attaches to X or not, whether W attaches to Y or not, whether W, things like that. If W links to X, if it goes like this, see, there are different things. We can go like this here, and the fourth side of the parallelogram is down here. Or we can go like this, and the fourth side of the parallelogram is over here. Or we can, let's see, there must be a third. Or we can go like this, and the fourth side of the parallelogram is over here. I don't think there's a fourth option. X to W and to Y and stuff like that. So I think these are the different options that we have there. So I think it's three. W to Y, yeah, that sounds right. Anyway, so let's count the different things. So down 2 over 3, down 2 over 3 would be one of them right here. Are they calling it Z? I'm going to call it Z. Z is at 4, 0 for one of them. If you join it up, you'll see what I mean. Like that. There's a parallelogram. Let's do it from Y to X this way. Up 2 over 3. Let's go up 2 over 3 like that. And then you have a new Z over here. This Z is at negative 2, 4. See, it's kind of a nice problem as far as they didn't call it WXYZ or WYZX or, anything like that. So it just depends. And then this one here is up 1, 2, wait, hold on. Up 1, 2 over 1, 2, 3, 4, 5. And up 1, 2 over 1, 2, 3, 4, 5. So that'll be Z at 8, 8. Am I making sure there shouldn't be a fourth one, right? There has to be. I feel There absolutely has to be. Hold on a second. Wait. No. Wait. Hold on. Boom, boom. Boom, boom. And I can't even find the third that I did before. And this one. Boom, boom. No, I think that's it. All right. 3 different ones. 4, 0, negative 2, 4, and 8, 8. 4, 0. 4, 0. Negative 2, 4. I hope there's not a fourth that for some reason I'm not coming up with. That it should be fine with those 3 points, the 3 unique ways to do it. 3 ways. Like that. I don't know why I'm having so much trouble kind of connecting that and saying, is that right? Mr. Robinson, is there another way you can do that and you're not picturing it? I need to pause and make sure. I need to be absolutely certain. Hold on. Okay, so yeah, I feel like those are the only way. I just keep drawing it. I feel like those are the only ways. If there's something else that I'm screwing up, my bad. Okay, let's keep moving forward. 2 more. Number 46. Oh, they're both proofs. Number 46, proof. Right equations. In the let's not look at 47 yet. In the diagram, segment EK bisects angle FEH, and FJ, segment FJ bisects angle EFG. Prove that, did they ever say it's a parallelogram? Prove that EK is perpendicular to FJ. Oh, they're markings that it's a parallelogram. Hint, write equations using the angle measures of the triangles and quadrilaterals formed. Write equations using the angle measures of the triangles and quadrilaterals formed. Okay. Okay. I'm going to copy and paste this over. They don't say use a 2-column proof. So I'm not going to do all this given stuff. I'm going to see if I can just work around this problem itself and see that I can go with what they're talking about. My thought, and I don't have a way to the answer, but my thought with strategy is I got like triangles that add to 180 and stuff like that. We need to prove that this is a right angle, basically, that it's 90 degrees. So I don't know where they're getting at in full. I say if this is X, and if this is Y, then this is Y because the bisector stuff. That means the whole thing's 2Y, whole thing's 2X. We do know, I don't know if this is helpful, that 2 of the X's plus 2 of the Y's equals 180 because it's so this is a parallelogram. So consecutive angles are supplementary. We know that. We also know that X plus Y plus the measure of angle P is 180. X plus Y plus measure of angle P is 180. Now, we don't yet know that P is 90 degrees. You have to remember that. We do not know that here. However, these are both 180, so we can also do something where we set these all equal to each other, like 2x plus 2y equals x plus y plus measure of angle P. I think I got it. If I subtract x and y over, x plus y equals measure of angle P. Now, if x plus y equals measure of angle P, I can substitute measure of angle P in for x plus y over here, like that. Probably should have began with that. You know, I probably should have began. Okay, I'm probably overdoing that part. If 2x plus 2y equals 180, I divide everything by 2, then x plus y equals 90. So let's go steps less than that. If x plus y is 90 and x plus y plus measure of angle P is 180, then I can substitute 90 right there. 90 plus measure of angle P is 180. The other thing I did was fine. I just think this works a little more efficiently. Measure of angle P equals 90 degrees. Therefore, P is a right angle. Therefore, angle P is right angle. Therefore, segment EK is perpendicular segment FJ. Cool. I was going to say it didn't have much to do with the parallelogram, but it did because the consecutive angles part. I think that was the only way that we used it. Okay, number 47, last problem. 2-column proof? It's a 2-column proof. Prove the congruent parts of parallel lines corollary if 3 or more parallel lines cut off congruent segments on one transversal, then they cut off congruent segments on every transversal. Draw them such that quadrilateral. Okay. 47. Well, I'm going to copy and paste that. I ain't redrawn that. because it's so to scale, I assume. They said draw them such that those are parallel. JQML. Where's Q? Oh, that? I don't know what they want me to do yet. I'm trying to get a good color. How about green? Here's JQML. In green. And in like kind of a lighter blue, I'll use what? GPKJ. GP. There, I can see that. KJ. Right there. So I have two parallelograms. What do they want? If 3 or more parallel lines cut off congruent segments on one transversal, boom, they cut off the segments. I think this is what they're talking about. Then they cut off congruent segments on every transversal. Draw KP and MQ, KP and MQ, such the quadrilateral this and this are parallelograms. Okay, now let me work this out without writing anything so you can follow along. I feel like sometimes when I do a proof, you're like, where are you going with this, Mr. Robinson? So let's see if we can plan this thing out. We're constructing a parallelogram here. We already know these are parallel. So we're constructing parallel lines, therefore we made a parallelogram. Parallelograms by nature have opposite sides congruent. So we know that that would be congruent to this, that would be congruent to this. These are congruent to each other, if that helps. And, oh, check this out. And these are congruent to each other. I wonder if we get to make a parallelogram right here. There must be something that talks about those somehow becoming parallel in some way to make its own parallelogram. I don't know how that's going to help us yet. But if that makes a parallelogram, that makes those congruent. I need to figure out that basically these are congruent. That's the goal. That's the trickery. How will I go about that with those congruent parts? I feel like, yeah, if you drew something there, you had a parallelogram. Therefore, that's congruent to that. And then that's a parallelogram with that right there. How do I know that I can state those are either parallel or congruent to the question? Anything about angles? I got an angle, parallelogram. I got parallel lines, which means these are corresponding angles here from those. No, I don't know those are parallel yet. Wait, no, yes I do. I know this is a parallelogram. So parallel, okay, so those are, well, they're not corresponding. But can I show those triangles are congruent for any reason? Oh, I don't know what to do here. Draw them such that this prove HK is congruent to KM. Given this, GJ is congruent to JL. I'm sorry, I'm picking this apart. I'm working through it best I think I know how, and I don't know how yet. These are congruent because the parallel things. These are therefore congruent. Okay, I mean, I can do enough to show those are congruent. Just now these are corresponding angles, things like that. I just don't know what that leads me to. Basically, I need to show the triangles are congruent by CP/CTC. I'm nearly there. I just need to now figure out how to work off this one. I guess I can say, because these lines are parallel, these are also congruent. So I can use a form of an angle side thing here. Either this set or the other set right there, and use a bit of an angle side proof and therefore CP/CTC. Okay, I think I got it. I just want to talk about, I want to figure out whether I should use P and Q, or I should use this HK, or I should use this one and this one, because those are parallel lines, and that's a single line. Okay, I think I'm going to use that one. That's more of actual corresponding angles. The other ones are kind of, they're not made up. Well, they are made up, but they're congruent. It's just it's not corresponding angles. Okay, so let's get into that here. Let's see if I can talk you through this. I might even draw in the other one again so I can keep writing here. So let's reconstruct what I was doing. So statements and reasons. Now I just got to figure out if I can write all the, construct this, it's a parallelogram, that, all that. It's the last problem, so I want to whiz bang through as best I'm able to. Is TED 2 still on? No, it's rolling credits. Statements, reasons. All right. 1, bunch of givens. Line GH is parallel to line JK. Oh, is parallel to line LM. And segment GJ is congruent to segment JL. Now that's already marked on that diagram that you see on the screen. So that's given. Okay. 2, draw, I'm going to draw KP parallel to GJ and MQ parallel to JL. This is by construction. So we're drawing ourselves new points there. We're going to force parallelness out of them. So boom and boom. I mean, that's all a single line. I'm sure I can use a single arrow for all of those. There's nothing wrong with just they're all parallel kind of together, if that makes sense. Boom, 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 boom. That's not going to matter. I just don't want the drawing to look more confusing than it already is. Because these sets are already parallel and those sets are now parallel, although those were single arrows on the other ones, I probably should have done double anyway. Then that means GPKJ and JQML are parallelograms by definition of parallelogram. I have two sets of opposite sides. Definition of parallelogram. Okay, if I have definition of parallelogram, I built all of that for a couple reasons. The main one I can first talk about is if I have parallelogram by definition, then I have opposite sides congruent. You know, these ones are congruent. Well, now these are congruent to each other in that sort of way. Literally, PK congruent to QM, but I first got to say that they are congruent in their own way for opposite sides. So segment GJ congruent segment PK, and then also segment JL congruent segment QM. JL congruent segment QM, because parallelogram opposite sides theorem, I think it was called. Parallelogram opposite sides theorem. That's his theorem. Believe it. That's his theorem. Now I want to say PK is congruent to QM. I'm going to start proving these triangles here are congruent to each other. Boom and boom, like that. So we have the marking that shows they're congruent, but we really got to say that there are. Because the reason we want these two triangles here is because they also include HK and K and MK right there. So if the triangles can be proven congruent, then those corresponding parts will be congruent. So 5, HK is congruent to KM now. Excuse me, PK is congruent to QM. PK is congruent to QM by the transitive property. You know, we kind of did that last thing before in that same way. I am doing the same skipping step thing that the book does. Transitive property of congruence. We already have the markings for it, but that's one part of these triangles that are congruent. Now we need to get two other sets. We're going to get corresponding angles, which we could have kind of done off the bat. Excuse me. Yeah, we could have done these corresponding angles off the bat right here. And I'm going to go ahead and state that one now that we're associating those triangles. Angle PHK is congruent to angle QKM, the ones I just labeled. I know it's kind of small. And let me do the other set of corresponding angles. This will be really small for me to do. Right here and right here. They're also corresponding angles that have parallel lines here, parallel lines there, through that transversal. So that's also another set of corresponding angles. So they're different transversals that we're doing this on, but PHK congruent to QKM, and then Q, whoops, not a different step. I'm just going to do this all in the same step. Angle PKH is congruent to angle QMK. This is the corresponding angles theorem. Because I have all of this, I now have congruent triangles in here. I know it's very small. I keep saying that, but I'm just acknowledging congruent triangles. I do have an angle side case of congruent triangles where I can say, there's two more steps, where I can say triangle, you can use any of these letters here. PHK is congruent to triangle, just keep it the same, QKM, by the angle side congruence theorem. And lastly, if those triangles are congruent, then corresponding parts are congruent, such as HK and KM. Segment HK, I wonder if this is how they kind of show that this is all true. It's congruent segment KM by CPCTC. CPCTC, this guy here is the same length as that guy there. Those are different lengths than, say, GJ and JL, but they are their own set of congruent parts there. Okay, now I don't know if that's how they used all the proofs and like Archimedes and stuff growing up in the day, but that absolutely works. And guys, that is the last problem. That ought to do it for this one. Thank you so much for watching. This is Mr. Robinson. I didn't know I was going to get this under 2 hours. Check out the description section down below. If you're at the end of this and you're like, there was a description section, I can go back to timestamps. Go ahead and find them. And I could have downloaded this. I can recopy all this down. Go ahead and do that. Get ready for some 7.3 later in the fold, whenever that is. Or check it out in the playlist if it's already done. All right, take care. See you in the next one.